Namaskar, welcome back. This was the last slide where we stopped. We were discussing about the significance of paleoseismology and active tectonics. So there are a few more slides on which we can have discussion on this, and then we'll move to the new topic. So about again further, the paleoseismology uh, is also a part of a broader field of earthquake geology. Usually we try to look at the extremely exclusive geology part, but as we say that other than the earthquake geology part, the paleoseismology also involves or includes the modern and instrumental earthquake data. We also touch upon the tectonics in a regional scale and all that, and structural geology, that is a branch of earth sciences. Historical surface deformation we also try to look at, but from through geomorphology. But now what we have, if you take for a couple of decades, then you have a very robust uh, technique which is available is GPS measurements. That is what we call geodesy. And then tectonic geomorphology, of course, it is related to the studying the morphology of the landforms uh, uh, generated by tectonic activities. There are many definitions, but all these definitions are from different uh, like research groups. They converge to the same part. Okay, so if you have the comparison of definition for paleoseismology and related fields, as or we can say allied fields, then we also say that it is like in British, they say the paleoseismology, and some uh, people will talk about that it is historical paleoseismology. Okay, so there are multiple definitions which are talk just to compare that. Okay, and then earthquake geology, paleoseismicity, neotectonics, and then you have like active tectonics. Some people will say morphotectonic. So morphotectonic is again part of the tectonic geomorphology we are talking about. Seismotectonic, the study of the role of seismic activities in tectonics, how it has been like influencing the overall landscape evolution and all that. So, and significance of the geological structures over there, and then what is the relevance of those geological structures in terms of producing earthquakes. Okay. So, like this is about the tectonic geomorphology part. So, there are many like allied, we can say the sub-disciplines which connects to the paleoseismology. So, it is not only just the one like we just look for the earthquakes, but we also talk about the landscape evolution and how the landscape change over the time. Okay, so the ultimate part is that uh, it helps us in understanding the neotectonic activities, and the neotectonic activity in particularly we try to bracket this as in like the activities which took place or the tectonic movements which took place during late Cenozoic era, that is during the transition of tertiary and quaternary. Of course, if we are talking about the active tectonics, then this is bit older tectonic movements if we have to confine to this period. Okay, that what the late Cenozoic era, and that is a transition phase of tertiary and then coming to the quaternary part. So it is quite old actually, but then also we sometimes we consider this as an neotectonic evidence to, and then try to understand and connect that. Okay, so this type of activities have been taking place since very long like span of time. Now paleoseismology also helps in knowing the regional pattern of tectonics and behavior of individual fault. So you can try to look at the regional framework and then individual faults also, how they are behaving in terms of triggering earthquakes and all that, that you can do. And the most important is that it has direct relevance to the society. So it directly helps society by giving needful information about the natural hazard. That natural hazard what we are talking about the earthquake. Okay, but kindly try to note that the earthquake can result into cascading your events. Okay, because it can result into your more like landslides that can trigger into the floods. Okay, so and as we have discussed about the tsunamis also. Okay, so it helps in yeah, providing needful information about the natural hazards, probability of and or the severity of the future earthquake in that particular region. So before 1980, if we take, okay, in most of the countries which are vulnerable to this type of natural hazard, that is earthquakes, and in particularly United States and USSR, this type of studies were solely based on the historical record. But now most workers investigate seismically active faults to undertake paleoseismic studies in both regional and site specific seismic hazards. So they are not talking just on the regional scale, but they come down to the site specific or the site of interest, and then they try to work for the better uh, evaluation of seismic hazard. And another part which we have been talking about, that they used to have work on solely on the data which was available in historical earthquakes. Okay, now suppose there is no data, no, that event was not recorded, any particular event was got like unrecorded during that time. So we may have sort of a gap of that information, and we don't get that information in the historical data, and we may underestimate the hazards. So this is another aspect that help paleoseismology help to bridge the gap between that non-availability of the data and then whatever the data is available. In most of the seismically active regions of the world, including Himalayan belt, many active fault zones have no historical records. Okay, for large magnitude earthquake, and that we discuss about the large magnitude earthquake that we are talking about 7.7 magnitude or 7.5 magnitude. So paleoseismic study is a common practice in many countries like United States, Japan, New Zealand, and if you take Italy. So they are having now. We can say that now India is also having very robust maps which are available based on the active fault and paleoseismic studies. And these studies can provide significant data, one towards recognition of individual paleoseismic event. Like, so this can help us in pinpointing, identifying the paleo earthquakes or ancient earthquakes preserved in sediments and on surface in terms of like in terms of the landforms. Okay, in form of landforms we can say. So landforms, so we have evidence on the surface, we have evidence in sediment successions. So behavior of individual active fault segment also, it can talk about that how this fault is behaving in terms of the seismic events. Okay, whether it is keeping quiet for very long and then slip resulting into the earthquake, or there are frequent earthquakes, in the sense not frequent daily earthquake or so and so, but we are talking about the span of the time interval is not very large. Okay, so how the fault is behaving, that also we can talk about. Rate of faulting, we can talk about the slip rate, and these all parameters are important for proper seismic hazard assessment. Okay, so based on the slip, you can calculate the magnitude, you can calculate that what will be the recurrence interval and all that. Okay, so the ultimate final application of this data, which is very important, and without that it is not advisable to go for the seismic hazard assessment. Okay, so this eventually helps in proper seismic, to undertake proper seismic hazard assessment. So paleoseismology itself, as I mentioned in the beginning, that it itself is an interdisciplinary field. Okay. So you use photogrammetry here, you use geomorphology. So you are using in photogrammetry high resolution satellite data, okay, and of course you try to generate 3D image of that terrain, and then you study the landforms, surface landforms. That is your geomorphology. Okay, then you have structural geology, then sedimentology, then soil science you are talking about, and dating part. Okay, you have like a lot of uh, different sub-disciplines, and that knowledge of those sub-disciplines should be there with you to undertake the paleoseismological investigations. Okay, so so the so yeah, the here what we are looking at, that right from the remote sensing part, you are talking about the landforms, then you are talking about the structural geology, fault, folds, joints, okay, and then sedimentology, you are talking about the environments in which those sediments were deposited, and whether the tectonic activity resulted into some change in the local environment or on a larger scale. Okay, then of course soil is important because the tectonic landforms will remain or will get exposed to the weathering process during the time of quiescence. Okay, so if there is no activity, then that will remain, and then soil formation will take place. So when we look at the sediment succession, we come across multiple soil layers. Okay, so that indicates that that surface remain exposed to weathering and then other processes which helped in forming the soil on that the then existing surface. Okay, then now we are having the dating of the material, to get the age of that particular sedimentary unit. Okay, so it is not, and like it is an interdisciplinary field. Okay, now this part of course we thought of that we will talk later, but there are like this is again related to after we uh, had in this Myanmar earthquake. So we tried to look at that, what was exactly what, how much was the length of the rupture, and what was the magnitude. Okay, so if you look at, because this one here is in like the fault which the magnitude, we had magnitude, and then said, then we looked at that. So these are the empirical relations which are available, uh, and based on which you can talk about that what will be the surface rupture, and these are the standard curves which are available based on different data sets. So these are all curves for different fault. Here the symbols shows that the circle and square and their triangle, they shows the that from the historical data as well as the paleoseismic data, and then whatever the earthquakes were been experienced in the last couple of decades. So those are been plotted, and based on that the empirical relation. So data is been used, the real data, okay, not the synthetic data here. Similarly, you can correspond this to the like moment magnitude and the magnitude here. Okay, so the earthquake the like your magnitude was 7.7. So that gives that how much was the surface length. Okay, subsurface rupture and the surface rupture. So that gives you. So it was somewhere over here. If you see that in 100, and so this was your 120 to 300 kilometer long rupture was there, and this was again like so this is related to your uh, 2025 uh, Myanmar earthquake. So with this we will stop here, and not stop here, but we will continue with the new topic now.